The challenge my team chose for the NAE Grand Challenge is providing access to clean water. The data we used was collected by an engineering company that has developed a multi-layering filtration device that removes contaminants and particles from the water. The first layer is used to remove large particles. The next few layers continue to sort out debris from the water until it has removed all contaminants and the water is pure. It is from the simulation of 300 water molecules taken at 26 timestamps that the data was collected from. Our team decided on this challenge after looking at the stark reality that is clean water. While it is something many people take for granted, it is also something many are unable to attain for themselves. In 2005, the Center for Disease Control reported that more than 800,000 deaths of children less than 5 years old was caused by poor drinking water. Imagine UH's own TDECU stadium, filled to capacity at 60,000. Then multiply this by 12, and that is how many children are dying from poor drinking water. It is the moral obligation of those who have the power to change these conditions to discover a way to get clean water to all parts of the world. Worldwide, approximately 780 million people do not have access to clean drinking water. Assuming 800,000 children have died each year, in the past 10 years, 8 million children have died from poor drinking water. The Center for Disease states that if water conditions were improved, 88% of the deaths could be prevented, meaning 7 million kids would still be alive. Our goal is to have a particle be chosen and to provide the trajectory of said particle. As the trajectory of flow is laminar, any changes in trajectory would correspond to blockage or contaminants. Next, our code allows the user to input a timestamp that then displays the pressure and velocity at a given time. It allows the user to track and see changes in pressure and velocity as time goes on. Having a large change, for instance, signifies poor flow or a poor filter or blockage. Here we have our code. And as you can see, we first need to input our data from the Excel file. We then have the constants of x high and y high that we need to convert our data to nanometers. Here we convert it to nanometers using x high and y high. We then ask the user to please input a particle number from 1 to 300 as disease trajectory. If the particle is greater than 0 and it's less than or equal to 300, it will calculate the trajectory of the x and the y. Otherwise, it will give you an error and you will have to input a particle number within the given parameters. We then pass it through the createFit function to graph the trajectory of the particle. Here is the function createFit. In the next section, we use the Navier-Stokes equation to calculate the pressure and the pressure gradient. We first ask the user to input a timestamp they want to see. If the timestamp is equal to 1, there will be an error as we are not able to provide information for this timestamp, given that the Navier-Stokes equation uses a parameter from before the timestamp and after, and there's nothing before 1. The timestamp given must be between 1 and 26, or you will get an error. Next, we set up all our variables for the Navier-Stokes equation, and we then pass it through our function fluid gradient, given here. In fluid gradient, we use viscosity, which is a constant for water, in kilograms per meter second. We must convert this to nanometers and picoseconds. We then use the Navier-Stokes equation to find the partial second derivative. Then to find pressure gradient, we multiply this partial second derivative by viscosity. Finally, to find pressure, we take the absolute value of the pressure gradient times the difference in x position, and then we multiply it by these constants to get it in kilograms per meter second squared, or pascals. We then print the pressure and the pressure gradient found. and we graph the pressure gradient as a bar graph. And then we graph both the pressure and the pressure gradient in line graphs for comparison. Our last section deals with velocity, x and y. We first ask the user to input a timestamp from 1 to 26. Depending on the timestamp, you will get different velocities. The error of this will come from not entering a timestamp between 1 and 26, as there's no values that can be calculated with those. We will then graph these on a graph for the x velocity of a given timestamp and print the value. And we will also find the average velocities. We will also continue to do the same for the y velocity and calculate the y velocity average and print it. When it comes to efficiency, while this is not efficient, there's no way we could find that we could calculate the velocities by adding 1 to each timestamp in between. Now, when it comes to the test case, we first run the program of the first section, and we input a particle to view its trajectory. Let's say 7. Here we have the given trajectory of water molecule number 7. We then move on down to our next section. Here we must first run the program and enter a timestamp we want to view. Let's say 5. Here it calculates the pressure of molecule 7 to be 4.490 e to the negative 19 pascals. It also brings up the graph here of the pressure gradient compared to the pressure. And down here, as you can see, it has written out the pressure of molecule 7 at timestamp 5 is 4.490 e to the negative 19 pascals. We then move on down to our last section for the velocities. We run the section, and it says enter a timestamp from 1 to 26. So I'm going to say 5. Here is the y velocity for all 300 particles at timestamp 5. Here it also shows the x velocity for all 300 particles at timestamp 5. We then see the average x velocity of 300 molecules at timestamp 5 is 1.32 Newton meters per picosecond, and the average y velocity of the 300 molecules at timestamp 5 is negative 0.01 Newton meters per picosecond. These equations and functions will run for all given values 1 to 300 particles or timestamp 1 to 26, except for the pressure equaling 1 in the second section. It's efficient and you can use it with any given test case. When it comes to limitations and applications of our project, you can apply this in many different scenarios, such as the Flint, Michigan water supply crisis currently going on in the United States. You can use this to see how much lead there is in the water and if it would be able to filter out in very small nanometer particles. You can also use this when it comes to traffic flow. You can use the time steps to see different times of the day, such as morning rush hour, afternoon, evening rush hour, or midnight. You can also use this when it comes to the flow of oil. However, it will have to change the viscosity and the fluid gradient. That is one of the limitations of this. It only includes the viscosity. It can only calculate pressure given that the viscosity equals a constant number. If it changes, however, you would not be able to calculate the pressure, but you can still calculate x and y velocities. You also cannot use the first time step in pressure, so you would not be able to know what possibly the pressure of morning rush hour traffic is like if you don't have any data prior to that in the same day. This data also can't show trend lines as it doesn't follow a straight path. All the numbers are scatter plots, so there is no way to use polyfit and to find a trend line to show a great average. Coming back, we hope that this data is able to help all those who need clean drinking water and to bring attention to one of the biggest problems the world faces and what people can do to help and solve it.